All right, so we're going to pick up from where we left off in class. So real quick little refresher, harmonic series we talked about is this series right here that passes the end-term test because then goes to infinity. This overall would approach a sequence value of 0. However, it's still diverged. So that's where we left off with. So that'll be a common series that you're going to want to know pretty well. So the next test we want to look at to determine if a series is going to converge or not is what's called, obviously here, the comparison test. And what the comparison test is saying is that if we look through here, if A sub n is the series that we're looking at, so whatever one we're trying to determine if it converges or diverges, that this will converge if there is a known convergent series. So by that I mean think of 1 over 3 to the n, which I think is one we're going to talk about here shortly. That's a geometric series that we know converges because the r value is a 1/3. So that's a series that we know converges. So if we could show that our series, A sub n, is less than or equal to a series that we know converges, then this would have to be converging itself. All right, converging means it has a limiting sum. And if that sum has a finite number, and the one that I'm concerned about has either the same number or values that are less than those terms, then it would also have to converge to a finite sum, a value smaller than the known series convergent sum. So if A sub n is less than or equal to a convergent series, we would know our A sub n series converges. In the same way or similar way, if we take our series and we converge it or compare it to a divergent series, I'm going to use D just to indicate that it means it diverges. If our series of terms are always greater than or equal to the same exact corresponding terms in that divergent series, then it would have to mean that our series would also diverge. If this has an infinite sum, that's why we're using the word D, because it diverges with an infinite sum, and our series is equivalent to that, or possibly even greater than that, all those terms, then overall our series would also have to diverge. All right, that's a comparison test. Where you want to be careful is, let's say we take our series and we compare it to a convergent series. If we get that to be greater than that convergent series, that doesn't tell us anything. This would be what we would consider inconclusive. And the reason for that is this convergent sum could be a sum of maybe 3. Well, this could still be greater than 3 and converge. It could just converge to a sum of 4. So if we end up being greater than a convergent series, it doesn't tell us anything. Same if I end up taking my series and comparing it to a divergent series, and we end up being less than a divergent series, this would also be inconclusive, because it could just mean that, yeah, this goes to infinity. This could just as easily go to infinity, but just go there a little bit slower than this one. All those terms might be a little bit smaller, but they could both still be diverging. So the relationship we're always looking for with this is our series is less than a convergent series, or our series is greater than or equal to a divergent series. So what all that means, in number 1, when we do the comparison test, what we're really trying to do is create a series that looks very, very similar to the one that we are working with so that we can compare them easily. So by that, I mean what I'm going to do, and the other thing we want to do is kind of keep either the numerator or the denominator the same. So what we're going to do with this first one, we're going to let the numerator remain a 1. And then what I'm going to do, we're going to look at our denominator here. All I'm going to do is get rid of that 5 so that I now have a series 1 over 2 to the n. The reason I want this series here is because hopefully we have now done enough of these here in the last couple of days of notes to know that this guy here is a geometric series, and the ratio of this would be 1 over 2. The numerator is always a 1, and we would be multiplying by 2 over and over and over again. Well, this is a geometric series then that converges. So I can easily take the series that we're working with and create a known convergent series by just dropping that 5 out. So if we're going to compare it to a convergent series, what we need to show is that our series is less than or equal to that convergent series. So if we now look at how these are set up, notice how the numerators are the same. They're both a 1, 1, 1. And then in your denominator, they both have this 2 to the n, but isn't this denominator here always going to be a little bit bigger than this denominator here? So if the numerators are the same all the time, and this one always has a bigger denominator to divide into that numerator, then what this then shows is that that series that we're trying to test is in fact smaller than the geometric series that we know converges. So we have shown that our a sub n series, this one, is less than this one, which is a known convergent series. So that's the comparison test. So because we can now show that, now we get into our explanation where we're going to say this converges. Then you're going to state whatever test that we know allowed us to say that it converges. In this case, it's the comparison test. And then what we would say is it is less than a geometric series with a ratio whose absolute value is 1/2, which is less than 1. Number 2, similarly, what we're going to do is keep the numerator the same. All I'm going to do is drop out this this minus a 1, so I'm just going to be left with an n. So notice again, we kept the numerators the same, and all I did to tweak my denominators, I got rid of this minus a 1. By doing that, what I've now created is this series here. In number 1, we created this series. That was the geometric series that we know converged. When we drop out the minus a 1 over here, what we now create is a series that we would know diverges. Right? So since this diverges, and the reason we know that diverges is because that is the harmonic series that you can look up at the top of the page, what we talked about really quickly at the end of the class period yesterday. So if this is a divergent series, what we need to have happen, and what we cross our fingers in, is that our current series would be greater than the divergent series. If we're greater than a divergent series, this series would have to diverge itself. So that's what we're hoping for. Numerators are the same. If we then look at our denominators, isn't this denominator always going to be just ever so slightly smaller than this denominator? So if the numerators are the same, and this denominator here will always be a little bit smaller than this denominator over here, then overall, isn't this always going to give you numbers that are bigger than this one? So that then does show that the series we're concerned about, we don't need to dot it in. We can say that that series is in fact greater than the harmonic series. So then we state this diverges, comparison test, it is greater than the harmonic series, greater than harmonic. The harmonic series speaks for itself. Whenever you say this, everybody knows that that then diverges. All right. Number 3, I realized in 5th period, can't do that one just yet. You don't necessarily need to cross that out. Maybe I shouldn't do that. It's one that we can revisit here in a little bit. But as of right now, we're not going to know enough to be able to do that. So go to number 4. And what we're going to do in number 4 first is, in order to tweak this, I'm going to leave my numerator the same. Leave that as a root n. And all I'm going to do is drop the natural log. So if you notice in the first couple, the easiest thing to do with these comparison problems, if it allows us to, depending on the problem looks, notice how we just drop out the little constant here, the little sum. We had a plus 5 there that we got rid of. Here we got a minus a 1 that we got rid of. We don't have that option in number 4. There's not just some number we can exclude. So what we did is we got rid of the natural log. Similar to the first 2 that we've done, the numerators end up being the same. So our root n on top remains the same in our new one. So numerators are the same. What we then want to do is look at our denominators. And if we look at our denominators, what we want to recall is the natural log function grows very, very, very slowly. Slower than the regular y equals x, which is kind of what this n is, the y equals n function. So if our numerators are the same, And this natural log number is always going to be small. It's going to grow very, very slow relative to the y equals n. Then wouldn't this natural log compared to the n always give us a smaller value? And if the numerators are the same, and this one's always being divided by a smaller number, then what that would mean is that the one on the left would always be greater than the terms of the one on the right. So we've done that, but if we now look at this one, this is not a nice series that we know diverges or converges. Up here, the first one, this was geometric. We know that converged. We look at this one here. This is the harmonic, and we know that that diverges. This is not one of those that we just look at and say, yeah, this is geometric or this is a harmonic. So what we're going to do with this one is we're then going to actually compare this to another one, and I'm going to leave the denominator alone. So I'm going to leave that as an n. And what I'm going to compare that to is the harmonic by putting a 1 on top. Now your denominators are the same. They're both n's. So it really is going to boil down to what happens in your numerator. Notice how the 1 is a constant and the root n, if we continue to graph root n grows unbounded. It's going to get bigger and bigger and bigger and bigger. So denominators are the same. The root n gets larger. The 1 never does. What we are now showing is that that middle series is larger than the harmonic series. So if this guy is greater than this guy, and that one is greater than the harmonic, then overall, the series that we are ultimately concerned about, we have just shown is in fact greater than the harmonic series. All right. So we can really pretty much, as long as we have the work shown, make the same exact explanation that this diverges. We did the comparison test, and what we now have shown, we would want to have this shown, justified, is that our series is greater than the harmonic series. All right. The comparison test is the one that people like to avoid. People tend to find this the most difficult. It's hard to kind of set up and understand these, but it is one that we are responsible for and that we need to be able to do. All right, if we go to the next page, we got a couple of more. This one is one of the nicer ones. It's called a p-series. A p-series is of this form right here. The one thing I do want to point out, it doesn't necessarily have to be a 1 on top of our series. So we have our infinite series. It just needs to be a number, a constant. And then notice what your denominator is. I have n to the p. So what the p stands for when we say p series, it's the exponent in your denominator right here, as long as you have a constant on top. So if I look at number 1 here, if your p is a 1, our function might look like this, 1 over n, because the p is the exponent of this n. Well, isn't this a harmonic series? So it's because that's the harmonic series, then this is going to diverge. If we go to number 2, if our p is greater than 1, so we do that over here, that would look like 1 over n squared. Our p is now a 2, greater than 1. When that happens, the p-series tells us that we should be converging. And then the last possibility in the p-series is if I have this 1 over n to the 1/2, so that the p is less than a 1, that 1/2 here, then that would tell us that this diverges. So pretty simple. Just another one, though, another layer of things that we need to understand and keep separate when we add these new tests in. And then the last one is what's called the integral test. What the integral test is telling us is, let's say we have a sequence of numbers, and what we're going to do is let that sequence get turned into a function that is now continuous. All right, then the series is going to get turned into, we're basically going to turn it into, remember those integrals we did when we had infinities in our limits? We're going to turn it into one of those. All right, so from approximation with the integral, with the Riemann sum, we're going to turn that into the exact when we did all these integrals. And if we can show that this converges, then what that would mean is the series is going to converge. So what that will look like with these first few. So what I'm going to basically show you, this is the harmonic series, right? So this should diverge. We're going to use the integral test and kind of show why this would diverge. So with this one, what we're going to do is we're going to turn this into an improper integral. So our lower limit would have been a 1, our upper limit would have been infinity, and we're now dealing with 1 over x dx. If you remember when we dealt with these, we want to make the infinity a b, so I'm going to erase the upper limit. That's a b. And what we're really finding then is what happens to this integral as our b grows unbounded towards infinity. So in the end, it's going to boil down to this limit. In the meantime, we want to do the antiderivative of 1 over x, which is a natural log of x from 1 to b. Plug in your upper limit, and then subtract, plug in your lower limit. We know this is going to be a minus a 0 here. And then what we now just have to calculate is, as your b gets larger and larger, so as the inside of our absolute value bars gets bigger and bigger and bigger, what happens to the natural log curve? So if you recall, when we talked about these, natural log curve does this. When b goes to infinity, that's really your x value. So as this goes further and further right, so this natural log curve, what does it approach? And if you remember, we said it does it very, very slowly, but the natural log curve does increase forever. So overall, this is zooming off to infinity. And because of that, just like we would have with the integral test, we would have said that that diverges. And that then with the integral test diverging would tell us that this series, as it should, because that's the harmonic series, should diverge. Okay, so that's the harmonic, the p series confirming that thought. So number 6, this should converge, right? This is a p series with a p that is greater than 1. So we could just say that converges right away, but it says show that, and then I want you to show that by using the integral test. I realize I did not put that in there. It should say that it converges. And we're going to prove it using the integral test. So same as we did in number 5, we want to turn this into an integral. So we're going to do the limit as b goes to infinity. The integral will go from 1 to b, and we're dealing with 1 over n squared, which should be an x squared. We're going to change that to our function f of x, and then our dx. Antiderivative would be x to the negative 1 over negative 1. We're going to go from 1 to b. Let's clean this up real quick before we substitute in. So finally we get natural log as b goes to infinity, plug in your upper limit, subtract, plug in your lower limit, takes us to here. You can then see that we have that minus a negative 1, so we know we're going to get a plus 1 here. And then what we now ask ourselves is, as b gets bigger and bigger and bigger, so as this denominator gets bigger and bigger and bigger, what would happen to this overall fraction as b goes to infinity? And what should happen is that that number should be getting smaller and smaller and smaller. So because then the improper integral converges to 0, or I'm sorry, to 1, that would then tell us via the integral test that this does in fact converge. Now long term, we just look at this and say, yeah, that's a p series, we know it converges, but I like doing the integral test to kind of prove it. All right, then real quick, add a 6b, because I want to prove that 1 over n to the 1/2 diverges. Because this is, again, the p series, anything greater than 1 is going to diverge. So let this be an n equals a 1. Let that be infinity. Set up your indefinite integral. Oops, make these x's. And then we're on our way here. So add 1 to that power. We'll get x to the 1/2. You're going to divide by 1/2, just say multiplying by 2. Plug in your upper limit. So I'm going to get 2 root b minus 2 root 1. we know over here, we're just going to get a minus a2. And then now as your b gets larger and larger here, the square root continues to get larger and larger and larger. And while we double it each time, it's going to continue to get even larger because of the 2 in front. So this whole thing is going towards infinity, like it should, because the p-series tells us that that should have been diverging. We can see that it does. So that's sort of the p-series and integral test altogether. The integral test just proving that that p-series is in fact valid. When we jump to number 7, one of the issues that people tend to have as we do an integral test is just remembering all the different ways that we did integrals. Sorry, these need to be x's as we turn this into a function of x. So 6x cubed over x cubed plus a 1. The first 3 that we did, 5, 6, and then that 6b that I had you add, those we could just look at and say what our antiderivative is. If we now look at this, this is not one we can just look at and know what our antiderivative is. So now we need to explore our other options of all the different ways we did integrals. The first being u substitution, and in this case, u substitution is our guy. So we're going to let our denominator be u, so this x cubed plus 1. The derivative of that is 3x squared dx. I need it to be a 6x squared dx. I currently have a 3, so all I'm going to do is double both sides. And we get the 6x squared dx that we need. So we'll go ahead and do our substitutions. Limit as b goes to, this should be infinity, so change that if you just copied what I had. So the limit as b goes to infinity. Our denominator is u. 6x squared dx we just created over here. And what 6x squared dx is equivalent to is a 2 du. And then we just put a 1 right here. We have now changed from x's up here, and we've now converted this into u's. So we need to use this right here to get our new limits. This is when we need our new limits. Our lower limit was a 1, so I'm going to take that 1, plug it in. New lower limit is 2. The upper limit will look weird because I'm going to take the b. I have to plug it in to convert it. That would be now b cubed plus 1. From there, we go ahead and do our antiderivative. So that's going to be 2 natural log of u from 2 to the b cubed plus a 1. Go ahead, substitute in your limits. So I'm going to get 2 natural log of b cubed plus a 1 minus 2 natural log of 2. So this would be okay. But then what we have to figure out is what happens as our b gets bigger. So as this gets bigger and bigger, you're going to cube it. That's going to make it larger. Then you're still going to be adding a 1. So what should be happening is this inside term here should be going towards infinity, getting larger and larger. And then what we're ultimately looking for then is, as that happens, what sort of functional values does the natural log take on? Natural log, we've already talked about it today, grows really slowly, but it does go to infinity. So we would say that this one diverges. All right. Now, the other thing to be aware of and that we want to be careful of is this idea that this is one of these that actually passes the end term test. So if I ask you, does n go to infinity? Actually, all of these are, right? But this one specifically, as n goes to infinity, the bigger degree is on the bottom. So this does pass the end term test, goes to 0. But what we have found is that even though it passed the end term test, all right, it would still overall diverge. All right. All right, and then 8, last one for this page. Turn that into the integral. Do your antiderivatives. You're going to get e to a negative x divided by a negative 1. But then instead of dividing by negative 1, just so it's easier to work with, we're going to make this a negative 1 from 1 to our b. Let's rewrite this first. So negative 1 over e of the x from 1 to b. Plug in your upper limit. Subtract, throw in your lower limit. We'll get a plus 1 right here. And then now we should understand that if our b gets bigger and bigger here, then what that's going to tell us is my denominator is going to grow unbounded, is going to get big very, very quickly, while the numerator is going to remain a negative 1. So overall, this should be going to 0, which means we would end up with 0 plus 1. So overall, this would converge. When you justify these, all you have to do is put the integral test, assuming that you've shown all the work. So as long as all of this is here, that would verify the integral test that you actually did the integral, then you can just state that's the test that we used. All right, so now last page. Where these get a little iffy now is we have a bunch of different options to choose from, and it really is up to you which one that you're going to use. What I will say, so let's create a little order over here. The first one that you are always looking for is the nth term test for divergence. So the nth term test can only prove that something diverges. So we really want to do this first, because if it fails the nth term test, we know it diverges. And it can save you some time. So if we go to number 9, let's do that first. What the nth term test is, again, this is what we did yesterday's notes. Don't do this to yours. But if I cross that out and it's no longer a sum and we're just talking about a sequence of numbers, what has to happen is that this guy here, as we go to infinity, has to have a limit of 1. So if we look, hopefully we agree that the faster growing function is on the bottom. So this definitely has a limit of 0. So what that means is it passes the nth term test. That's somewhat unfortunate, because if it fails the nth term test, you're done. You would just say that this series diverges. But when it passes the nth term test, it's kind of like the harmonic. This passes the nth term test, but it still diverges. So we need to continue on. So the second way that we did these, second type of thing that we dealt with, is a geometric series. So what we would want to look at here is look and see if this is in fact a geometric series. So hopefully we have done enough of these that we can look at this and say, yeah, this is a geometric series because we have this n as the exponent. And we would hopefully recognize then that the ratio for this geometric series would be 1/10. And we would then understand that a ratio of 1/10 in regards to converging or diverging would tell us that this series converges. And then we would say why, because it's a geometric series. With a ratio whose absolute value is a 1/10, which is less than a 1. All right. All right, 10. Same thought process where we're going to ignore this initially, and we have to pass the nth term test. So this is as n goes to infinity, this function here has to go to 0. Well, if we look at that, this is old. If we look at what our exponents are, they're both a power of 1. So that means our limit should be the coefficients, so 1 and 1. So this has to have a limit of 1. The nth term test tells us this has to go to 0 for us to have any chance of converging. So because our limit is a 1, what that allows us to conclude right away without really any other work is that right away we can say that this diverges. And then you would say test. And then we have to tell what the issue was. And that is, as n goes to infinity, our general term, the a sub n here, what I have highlighted in blue above, has a limit of 1 and not the 0 that we know it has to equal in order for this to have any chance of converging. All right, so kind of in order of which we've done them. Nth term test, geometric, that was the previous set of notes from yesterday. When we look at number 11, same thing. Make sure it passes the end-term test. It should, because our faster growing function is on the bottom. So because of that, this should overall have a limit of 0. All right. So pass the end-term test, so that just means we need to continue on. That doesn't necessarily mean it converges, but we should hopefully look at this. This is geometric. This is geometric. And then it's our little which function grows fastest idea. Since the base in your denominator of 3 versus 2 is faster, this does pass the nth term test. As n goes to infinity, the faster growing function is on the bottom, so this overall has a limit of 0. So, pass the nth term test, which is again somewhat unfortunate, because that means we need to continue on with our other thoughts. So, look to see, is it geometric? And hopefully we can see this is geometric. They both have exponents. And we would then hopefully understand our numerator is repeatedly multiplied by a 2. Our denominator is going to be repeatedly multiplied by a 3. So this is a geometric series. And since this is less than 1, this should be a geometric series that converges. So we say converges, geometric series, and then state that this has a ratio whose absolute value is 2/3. That is less than a 1. All right. All right, number 12, 1 over n, natural log of n. As we look at this, let's first make sure it passes the n-term test. So as n goes to infinity, the faster growing function is on the bottom. So this definitely passes the n-term test, so it goes to 0. So that kind of sucks, because then that means we need do a little more work. So the next thing we want to understand is it a geometric series? Hopefully, if we're understanding that number, or I guess it's number 9 is, number 11 is, that if we understand those are, then there's no way this one is a geometric series. This doesn't have a base raised to a variable power. So we got to investigate some other options. So if we go to some of our other options, the first option that we talked about today was the comparison test. So in 5th period, actually somebody said, let's try to compare it to 1 over n, because I can easily turn this into this. So that's a really good thought, because all they did is they got rid of this natural log of n to create a 1 over n. And the reason 1 over n is nice to compare it to is because we know this is the geometric or the harmonic series. So we know that this is a divergent series. Our issue, though, when the person brought it up, and bringing it up is good, but our issue is it has to be greater than a divergent series. So the one that we're testing better be greater than a divergent series. But if we look at this, if our numerators are always a 1, isn't this denominator always going to be bigger with the same exact numerator for both? So if this is bigger, what really happens is that this number overall is going to be smaller. And being smaller than a divergent series doesn't mean anything for us. So while that's a really, really good thought, it doesn't work in this case. So we're going to skip the comparison test. That doesn't do us any good. If I ask you if it's a p-series, there's no way that's a p-series, because a p-series would have to be like 1 over n to the 4th. We wouldn't want this natural log here. So our only other option is the one that most people try to avoid, because it requires the most amount of work, is the integral test. So turn this into an improper integral from 1 to infinity and 1 over n ln of n. Actually, let's make that upper limit of b right now. And then these should be x's also. So we're going to make this a function of x and then see how this works. So let your u be the natural log of x. Our du then nicely is 1 over x times dx. So as we go to set this up, I'm going to have the u in our denominator, that's the natural log of x. And then the 1 over x and the dx I've created. And I can get rid of it by just placing the du there. We need our new limits. So take your 1, plug it in here. Natural log of 1 is a 0. Take your b, plug it in here, and you're going to get the natural log of b. Find the antiderivative from 0 to the natural log of b. Plug in your upper limit, so I'm going to get the natural log of the natural log of b minus the natural log of a 0. And then we have all kinds of problems here. But just go in order. What's going on here? If b is going to infinity, so if this gets bigger and bigger and bigger, then the natural log of b, this guy, would also continue to get larger and larger and larger. And then ultimately that means this natural log, as we go further and further right, as x's go to infinity, this whole value then overall goes to infinity. So this would diverge. And again, as long as you say, or as long as you have the work to justify this, all we need to say is the integral test. All right. The good news for all you guys right now is while there's still 3 problems on the paper, that actually gets us finally caught up to 5th period. That's where they left off today. So we're going to stop right there. And then that will kind of get you caught up to where they're at. Actually, yeah, we'll stop right there. I won't kill you too much here on your day off. So with that, if you have any questions on any of this, check in with me. We've got a little time before you're going to have to do any sort of a quiz or assessment on this. So if any of that's not making sense, you have the video now to kind of look back, or you're certainly welcome to catch me on a morning during 2nd period. All right, that's all I got. Have a good day. We'll see you guys.